Hello and welcome to my video presentation for HCI 587. I'd like to talk about a fit assessment of GOM's prediction model applied to a case study called the Model Human Processor and the Older Adult, Validation and Error Extension to GOMS in a Mobile Phone Task. So this study was actually done back in 2006 by a woman named Tiffany Jastrzemski. She actually now works for the Air Force as a cognitive research scientist for the Performance and Learning Models Lab. My search for material, which ended with her paper, sort of covered a pretty wide gambit. I started with a premise of usability, above all, and I looked for an underserved section of the population. Eventually that led to seniors and focusing on their interaction with technology. I followed a lot of unhelpful avenues in looking for something to present on. Most of what I found was tied to pharmaceutical studies. For instance, those tied to mental clarity, mental recall, increased mobility, etc. Also many purely mechanical assistive devices, which helped with dressing, bathing, walking, and driving. I started having more luck when I looked at mobile devices as a whole category in and of itself, and assistive technology designed to support aging in place. Mobile phones are actually a really big part of that aging in place movement, as well as home automation. Home automation, when it is specific to the elderly and disabled, is actually called assistive domotics. And there have been big advances lately in terms of security, emergency assistance, reminder systems, medication dispensing, and robotics. We've got robots now that will do household chores, that will prepare meals, and do a lot of the above in terms of security and medication reminders, things like that. I settled on this dissertation as it took the traditional implementation of GOMS and made it more effective as a tool itself, in order to better estimate the effectiveness of any task and device measurement necessary when designing for the elderly population. The dissertation takes the baseline Card-Morn-Newell Model Human Processor, MHP, from 1983. It takes that model's perceptual, motor, and cognitive parameters and modifies those parameters to better model older adult usage. This modeling process was then used to model older adult performance for task completion on mobile devices, including delivering predictions when errors would likely result in these processes due to cognitive workload, hardware design, and software design. Next, these predicted errors were then classified for ease in modeling, and the likelihood of their occurrences was also modeled, based on what's already known about human performance. This set of predictions was then analyzed using a modified GOMS model, which revealed no differences between the modeled error predictions and actual human production of the errors. I should say no significant differences, across all types of errors in a wide spectrum of ages. The author points out that the majority of cognitive psychology theory largely relies on data that's been generated from studies that enlist younger adults. Given the growth curve of the percentage of the population that is aged 65 plus in years, this is an ongoing and increasingly problematic situation. If you give me a second, I'm going to show you what I mean. So let's take a look at the chart here. This shows the number of people 65 years and up, ranging from 1900 to the projected year of 2030. On the left, we've got population in millions, and along the bottom, of course, we've got our years. That's pretty staggering. Back in 1900, there weren't that many people that were that old. Simply disease, predation, lack of vaccinations, etc. As the years go by, we see more and more percentages, the higher and higher percentage of people reaching their 60s and then 70s and 80s and 90s. I myself have had grandparents up until their 90s. Okay, let's dive in. One of the first efforts to adapt modeling parameters for the senior population was made by Charnas and Bosman in 1990. As a side note, Charnas was actually this author's doctoral advisor. The limited data available at the time resulted in less than optimal estimates for senior abilities, so cognitive modeling based on that produced parameters weren't really useful. The author's approach of building an adapted model human processor yielded more useful parameters. The first part of this was coming up with means and standard deviation values for useful parameters, and that consisted of taking samples of numerous studies which represented the senior population in each round of analysis. She points out that in the original MHP model, the parameters didn't come from a cross-section of studies. Instead, most estimates of parameters came from 2 or 3 studies. Also, back then, the estimation wasn't statistically valid, as sample sizes weren't really considered. Her approach used weighted sample sizes, and so was a little bit more valid. Reasonable samples of studies were systematically collected for inclusion in each meta-analysis, in order to adequately represent older adult capacities and limitations. In Card-Morna-Newell's original model human processor, parameters didn't stem from this methodological search of studies, and many estimates were based on only 2 or 3 studies. So the ultimate goal of all this preliminary groundwork was to provide generalizable older adult performance parameters to designers and engineers to simulate older adult performance, and of course to be able to make predictions across varying design specs and tasks, with the ultimate goal of producing optimal designs for older adults. If you're curious how this set of comparative task time estimation data was gathered, you can check out Hunter and Schmidt from 1990. They have a method which reportedly offers better flexibility to generalize findings even beyond a set of included studies and form base-level parameters for the senior population. Now let's take a look at some of those parameters being modeled and compare Card-Morna-Newell's data from 1983 to that data found by Jastrzębie and Charnas. On the left, you'll see the parameters like eye movements, visual image store, cycle times, etc. The second column contains younger adult estimates based on Card-Morna-Newell's 1983. And the third column is the older adult estimate based off this particular study. The ratio of old to young is shown in the fourth and last column. Interestingly enough, in some areas there's very little difference, where in others there's a huge difference. One area that doesn't differ very much is the pure capacity of working memory. You'll see that younger folks can tend to keep 2.5 items of memory, and older folks tend to keep 2.3 items of memory. So it's very, very close. On the opposite end of the scale, the cycle time for the perceptual, motor, and cognitive processors is anywhere from 1.5 to 2. So it's remarkably slow. So a task that takes a 20-year-old subject 10 seconds to accomplish using their perceptual, cognitive, and motor skills will likely take a 70-year-old 1.5 to 2 times as long. This is before taking into account the impact of working memory capacity on tasks with a lot of moving parts. For instance, programming a DVR, preparing a complex meal, or recalling the specifics around whether medication has to be taken with food, in tandem with other medications, or exclusive of other kinds of food. Conversely, the ability to consistently remember a smaller amount of objects, again, is almost the same. When we're designing tasks and task sets for universal usability, the diminished memory capacity of a senior towards keeping many elements in memory would indicate that the limiting element concurrency in a user's memory would be well advised. Mobile phones were chosen as an appropriate venue for testing here due to the variety of devices, the ubiquity of their adoption across cultures, incomes, ages, and geographical circumstances. A statistic for you. In 2004, 30% of adults claimed that the cellular telephone was their most hated invention, but also the one they were most unable to live without. Considerations that are, of course, particularly important in assessing overall usability include the physical size of the device, size and arrangement of physical and virtual controls, as well as the values that we could apply from the LEMES, the LEMES framework, and that's from Nielsen in '93. That stands for learnability, efficiency, memorability, errors, and satisfaction. Essentially, how easy is it for someone to learn a device? How efficient is the device at helping the user perform their tasks? How memorable is the device? So if someone comes back to their phone after not using it for 3 weeks, will they still be able to remember how to use it? How does it handle errors, and how many errors does its design tend to cause? And overall satisfaction. How happy is someone with the device or the product? The typical task that the author used in this study was text entry. So the test participants entered names and numbers, appointment reminders, they sent text messages, emails, and browsed the web. Interestingly enough, almost twice the amount of 30 to 49-year-olds used text messaging as those aged 50 to 64, and this was in 2006. So the actual study, she took her study methods from a model-based evaluation of the Kyocera 2325 mobile phone done in 2004. That particular study tried out several different prediction models. So let's go through those. Fitts' law was tested out. It performed very poorly. They determined that was because it didn't really capture the visual and cognitive processing elements, just motor. Thus, it underestimated time on every task. ACTR did a little bit better and came close to rivaling GOMS in their studies, but it made assumptions about certain actions, namely the scroll versus selection actions, and they were incorrectly judged to take longer. GOMS produced the most accurate predictions. Basically, they came within 2% of actual user means. The method was to test older and younger users in specific tasks on specific mobile devices and compare their results against GOMS simulations implementing MHP parameters for older and younger adults. The hypothesis was that the predictions for older users would be as accurate compared to the simulations run by GOMS as the predictions for younger users based on GOMS would be to the actual user's performance. The study also predicted that in both human performance and GOMS modeling, the most efficient and accurate results would be found using the device with the least complex design. Larger buttons, larger display, etc. Kind of makes sense. So, of course, the question to answer here is GOMS appropriate to analyze this dissertation? Quickly reviewing GOMS, we know it's useful in determining how a virtual user would perform a task in a virtual system with a specific set of procedures. The constraint being that the user can routinely perform the task in question, i.e. they're an expert user. Typically, the individual steps are broken down to the keystroke level, and when you add up the time it takes to complete all those itemized micro-actions, you can often predict more or less effective strategies based on whether the goal was speed or accuracy. This is probably a good time to reiterate that knowing your user is paramount in design. Older users consistently prioritize accuracy over speed. This is important to know. This is likely in part due to no longer being in the workforce. What is good about GOMS? GOMS excels at showing the impact of very granular units of time and how the sheer volume of a minor procedure, as it's used many times in a higher level task, can seriously impact the speed of task completion as well as the error rate. Why the error rate? Well, if you think to any sluggish seeming system you've ever used, when that button doesn't react, it doesn't give you feedback, you'll probably hit it 5 more times. So sluggish seeming systems can stimulate overwork and error resulting behaviors. GOMS also gives us meaningful explanations for the predictions that it makes. So it lets designers zero in on the critical path delays, or more importantly, in our case, how task performance might differ between simulated users with differing abilities. What's not so good about GOMS? GOMS isn't very good at predicting errors in human performance and the impact that they would have. Despite being billed as only valid for expert user modeling, Card, Moore, and Newell noted that when comparing the expert model and the expert human in 83, about 25% of the total task duration was spent detecting and recovering from errors. This is an expert user. The bigger the problem, the longer the task took, in increasing orders of magnitude. So basically, GOMS isn't great at modeling errors in routine and expert performance. Some provision for error was provided in their 1983 release, but some assumptions were made. That error detection occurred immediately after the error was made, that the type of error was correctly identified, and that the failure automatically generated the correct recovery goal. The recovery goal is when you've got a primary goal, you make a mistake, you shift onto a recovery goal to recover from that error. You have to backspace, you have to delete a word, you have to find where your cursor should be. Once you've completed the recovery goal, you can move back to the primary goal. Also, GOMS assumes a resumption of normal task recovery, task execution after error recovery. So the effect of working memory between different users really isn't taken into account. If you're 20 years old, you can pretty much stay on task. If you're 70, you're going to forget where you are, you're going to have to resume. It might take you longer to resume. All that said, GOMS has actually been extended by adding more error-aware methodology, something called Error GOMS, or eGOMS, put out by Wood in 2000, succeeded at providing a general framework for error recovery. This augmented form of GOMS can account for problem-solving failures and skill-based failures, so it's a lot more appropriate to use in this type of situation, where you really need to account for a difference in 2 different user groups and their problem-solving failures and their skill-based failures. One of the many tasks that the test participants had to do was enter text strings of varying letters and words. It was observed that both young and old users were producing errors when entering the letter S in text. They figured that this might be because younger adults rushed too quickly and might misapply a common sense rule for entering the last letter. Typically, mobile keys possess 3 characters, so younger adults might assume that the last letter on a key would require only 3 presses. So instead of correctly calculating that the letter S needs 4 presses, younger adults may be more likely to press the button 3 times and stop, instead of supplying the 4th. Older adults also are hypothesized to have problems, but for an entirely different reason. Gom's analysis indicated that older adults may have difficulties pressing the same key multiple times rapidly before a phone's key timeout period shifts the cursor to the right. A key timeout period is basically the length of time after you've pressed a key before the phone will automatically move the cursor to the next spot in the array so that you can put a new character in. Given 2 different timeout periods across 2 different devices, 1 second versus a second and a half, Gomes predicted the issue to be a lot worse on the phone with a lesser timeout period. Here is a chart showing what I mean. Gomes' task analysis was able to show why the elderly made this error more than the younger test participants, and it was able to show why one device versus the other increased the impact of this kind of error. Other models would be unlikely to catch this due to the decreased level of granularity in the analysis and the lack of taking into account cognitive, perceptual, and motor aspects. Designers can take from this that older users need more time to press the same button 4 times than younger users, and that adjusting the key timeout to accommodate both old and young users, the error rate could be reduced across the board. You can extrapolate that this type of finding would result in this type of insight in many, many different cases. I do believe that Gomes is an appropriate model to use in this particular dissertation. It was applied well, and it was extended when it was found to be deficient in a certain area, specifically in dealing with and predicting the effect of errors.